in this section of the book, it may seem like we're backing up. We started with wanting to approximate sums, kind of continuous sums, and so we developed the notion of the Riemann sum, and we looked at Riemann sums for estimating various quantities, and then we took limits of Riemann sums to define the definite integral. And then we found that, well, calculating definite integrals as limits of Riemann sums was tedious. It's very, you have to pick partitions, and you have to calculate Riemann sums and take limits. It's painful. It's long. It's slow. And then we had the fundamental theorem of calculus, which makes things better. The fundamental theorem of calculus lets us calculate limits of Riemann sums easily because we don't explicitly calculate a limit of Riemann sums. We appeal to the theorem that tells us that the definite integral, that we can calculate it if we can produce an easy antiderivative of the function that we're integrating. That's great. But what do we do about definite integrals that we care about where we can't produce easy antiderivatives? That's a problem, and there are important integrals that involve functions that we can't easily produce antiderivatives of, functions that don't have elementary antiderivatives, antiderivatives that are finite kind of combinations of the functions that we use all the time. This causes a problem, and so we have some approximation techniques for approximating the value of definite integrals, and you would think, well, of course, the Riemann sums approximate definite integrals. It's true, but we'd like something better than Riemann sums, and that's what this section is about. So, as an example of an integral that we care about, for which we cannot produce a nice antiderivative of the integrand, I'll give you the integral from 0 to 1 of e to the minus x squared dx. This type of integral is important in probability and statistics, and yet it's a theorem that e to the minus x squared has no elementary antiderivative. There is no nice, as I said, finite kind of combination using addition, subtraction, multiplication, addition, subtraction, multiplication, and division, and composing functions and extracting roots and sines and cosines. Anyway, there's no nice formula for an antiderivative of this, and yet we'd like to approximate it. How do we do that? Well, I'm going to talk about 3 different ways. One of them is a Riemann sum, and then I'm going to compare that with 2 other approximations. What I'm going to do, though, is instead of looking at these approximations for this integral, which is the kind of integral we would actually care about, I'm going to look at these approximations for an integral that we can actually calculate explicitly using the fundamental theorem. Why would I do this? Why would I use these approximation techniques on an integral where we don't need them? So that we can actually see how much error there is in the 3 different approximations, and so that you can appreciate when one of the approximations is better than the others. But keep in mind, this is not the kind of integral that we really care about approximating. We care about using approximations on integrals like the other one, the integral from 0 to 1 of e to the minus x squared dx. We're just using this so we can actually kind of see how good or bad these approximations are. So I want to approximate this 3 ways. I'm going to approximate this integral 3 different ways. Before I approximate it, we could just go ahead and use the fundamental theorem and evaluate it exactly. This is 1 over x squared is the same as x to the minus 2. Use the power rule for producing antiderivatives. You add 1 to the exponent, divide by the new exponent, and you evaluate as x goes from 1 to 2. So you put in 2 and you get minus a half, and you subtract what you get at 1, which is minus 1. And so you get plus 1 minus a half. We get a half for the exact value of the integral. In fact, it seems silly, but let me go ahead and write that as 0.5 because we're going to get decimal approximations from our 3 different methods. and we'd like to compare them with this decimal. That's the exact answer. All right, how can you approximate this? Well, one way is with midpoint Riemann sums. So the first way that we're going to look at, midpoint Riemann sums. All right. So let's recall what this means. So first we take the interval that we're interested in. So let's set up notation for the general problem. We have some integral from a to b of f of x dx. I'm going to assume that a is less than b. And I want to remind you what the midpoint Riemann sum means. So what you do, a Riemann sum, well, we're looking at the closed interval from a to b. And we divide that interval up into n subintervals of equal length. So, so you divide the closed interval from a to b into n subintervals of equal length. What would that equal length be? Well, the length of the whole interval is b minus a, and you've divided it into n subintervals. So of length delta x, which is b minus a divided by n. Great. And then you have the endpoints of your subintervals. So the partition of the interval from a to b, the set of endpoints of the subintervals. We have our first endpoint of a subinterval is just a. You start at a, and then you go up by delta x each time. So x sub 1 is a plus delta x, which is b minus a over n, but I'll just write delta x. X sub 2 is a plus 2 times delta x. You go up by another delta x. So in general, x sub k is a plus k times delta x. And in particular, that means that x sub n is a plus n times delta x, but then you use that delta x is b minus a over n. And the n's cancel and you get a plus b minus a, so you get b. Well, that's good. We want our last x sub n, the last point in our partition, to be the other endpoint of the interval we're interested from a to b. All right, so we get this partition. We partition the interval from a to b into n subintervals of equal width, or equal length. And then you pick sample points in each subinterval. And you form the Riemann sum. In the midpoint Riemann sum, those sample points are the midpoints of the subintervals, the midpoint Riemann sum. And so what you get is you evaluate the function that you care about at the midpoint of each subinterval. And then you multiply times delta x and you add. But since delta x is the same each time, we can factor that out. And you get delta x times the value of the function at the midpoint of each subinterval added together. Well, how do you get the midpoint of the first subinterval? Well, you add x0 and x1 and divide by 2. So this is f of x0 plus x1 over 2 plus, and then this just keeps going. Each time it's the sum of the two endpoints divided by 2 to get the midpoint, and then you evaluate f there. This is the midpoint Riemann sum for n subintervals of equal length or width. Great. We did We could have and we did look at this a long time ago. But what I want to do now is try to come up with some rules, some approximations to the integral that are not Riemann sums. So what I'm saying is we can use this as an approximation to an integral, right? I mean, it's a Riemann sum. The integral is a limit of Riemann sums. So we expect this to be approximately the value of this midpoint Riemann sum. What does approximately mean? Well, it means approximately. There are some theoretical statements about the bound and the amount of error in using this as an approximation. They're in the book. I am not going to talk about them. But what typically happens and what you expect to happen is that as n gets bigger, so you divide this into more subintervals, your approximation gets better. Certainly in the limit, if you have a continuous function, this has to converge to this integral, which means if somebody tells you how close they want you to be, you can pick n big enough to make this that close to this integral. But that doesn't necessarily mean every time that n gets bigger, the approximation gets better. But we do kind of treat it that way, that bigger n's we kind of typically think should give us better approximations. All right, that's one way to approximate the integral. What's another way? Well, let me draw a graph, draw a picture to motivate this. I'm going to go ahead and state all three ways before I actually calculate anything. So what's another way of approximating an integral? Well, let's picture, I'm going to draw a picture where I've kind of assumed that f is always positive, just to make the picture nice. The integral of f of x from a to b is represented by the area under this curve, under the curve and above the x-axis between a and b, so above the interval from a to b. How could we hope to approximate this area? Well, I gave away the name. I am trying to derive the trapezoid rule or the trapezoidal rule. People say either one. So again, it relies on dividing the interval from a to b up into the same subintervals that we had for the midpoint Riemann sum. So you still have, let me just go ahead and call them x0, x1, xn minus 1. So what does the trapezoidal rule do? Well, instead of looking at a rectangle of a particular height, like midpoint Riemann sums, take rectangles whose height is given by the value of f at the midpoint of each subinterval, it doesn't use rectangles at all. It uses trapezoids. What does it do? In the trapezoidal rule, you look at these points determined by the endpoints of the subintervals, and you connect them with lines. So what this means is between these x-coordinates, or the points that you get from these x-coordinates, you're approximating the curve with little line segments. So between x0 and x1, instead of using the curve itself, you use the line segment as an approximation to the curve. And between x1 and x2, you take a new line segment between those 2 points, and you do these approximations of the curve by line segments, and then instead of actually integrating, you add up the areas of the trapezoids. And so this is not a Riemann sum. We are not adding together like areas of rectangles evaluated someplace. I mean, they could work out to be the same as a Riemann sum, but that's not how we're deriving it. and it is not, it's not set up as a Riemann sum. If it equals some particularly nice Riemann sum, that's a coincidence. So, but we know the area of a trapezoid. It's 1/2 the sum of the bases times the height. Now the height would be, well, this width down here. So the height of the trapezoid, what one normally refers to as the height, is actually just delta x. So the area of the trapezoid, of a single one, so the area of a trapezoid, so let me say the first trapezoid. Area of the first trapezoid would be this height plus this height divided by 2, 1/2 the sum of the bases, times the height. So it's 1/2 f of x naught plus f of x1 times delta x. What's the area of the second trapezoid? Well, it's 1/2, and then the bases here are f of x1 and f of x2. Times delta x. And then you keep doing this for each trapezoid until you get to the nth trapezoid. And there's a reason I'm writing out all of these, or this many of them. And then you add these together. What happens when you add these together? Well, each one has a delta x over 2, so we'll put that out in front. You get a delta x over 2, and then when you add these together, you get f of x naught plus f of x1 plus another f of x1, so you get 2 times f of x1. You'd also get 2 times f of x2 because the area of the next trapezoid would have an f of x2 plus f of x3. So you'd get f of x2 again, and so you get a 2 f of x2 in your sum. And you keep doing this. The area of the nth minus first trapezoid you'd have an f of x sub n minus 2 plus f of x sub n minus 1. So you'd get 2 times this also. But then when you add this part, you only get f of x sub n once. There's no overlap on the f of x sub n term and no overlap on the f of x sub 0 term. But all the other terms, you get f of xk twice. Unless k is 0 or n, you get f of x1 twice, you'd get f of x2 twice, you'd get up to f sub x sub n minus 1 twice, but then you only get f of x sub n once. So the trapezoidal rule, our second way of approximating, looks similar to a Riemann sum, but it's not. Our second way of approximating, the trapezoidal rule, the integral is approximately delta x over 2, and then f of x naught plus 2 times f of x1 plus 2 times f of x2, and you just keep adding 2 times plus dot 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 plus 2 times the next to last, f evaluated the next to last element in our partition, and then f of x sub n. So I'll say it again, you get f of x naught and f of x sub n with just a coefficient of 1, but then you get 2's for all the others. This is the trapezoidal rule. Again, there's a theoretical kind of upper bound on the amount of error in the approximation. But again, like the Riemann sum, the midpoint Riemann sum, what you expect to typically happen is as n gets bigger, the approximation should get better. If you look at the theoretical bounds that are in the book, what you'll see is the upper bound on the error in the trapezoidal rule is double the upper bound on the error in the midpoint Riemann sum rule. That means that typically you expect the midpoint Riemann sums to give you a better approximation than the trapezoidal rule. That is not necessarily true. The theoretical bounds on the error are bounds on the error. They're not the actual amount of error. And now I need to kind of say something philosophical. In general, you can't know the error exactly in these methods in any nice way because, think about it, we're trying to approximate something that we don't know how to calculate exactly. I mean, not in this one we know how to calculate exactly in this example, but the value of these methods is to calculate integrals that we cannot get exact values for. Okay. But if we have an approximation and we know exactly if we could calculate in some nice way both the approximation and the error in the approximation, then we would simply take the approximation, adjust it by the amount of error, either add or subtract the amount of error, and then we'd have the exact value of the integral. So it's unrealistic to expect that we will have nice formulas for exactly the amount of error in the approximation. What we have are upper bounds on how much error there is, but if by some coincidence, well, not even a coincidence, it's possible that in specific cases, for specific functions, for specific limits of integration, for specific n, the error in one of the approximations is much better than the bound. In fact, that happens in this example. The errors are better than the bounds. But it's possible that the error in the trapezoidal rule could be less than the error in the midpoint Riemann sum rule. You just don't expect it to happen that way. All right, that's the trapezoidal rule. It's at least as easy to use as midpoint Riemann sums. In fact, it's slightly easier because we don't have to calculate midpoints of subintervals. We actually use the explicit x's that we get from the partition instead of having to add x naught, or having to add xk and xk plus 1 and divide by 2. And then there's Simpsons Rule. This is Simpsons Rule is no harder to use than the trapezoidal rule. It's and yet it's stunningly more accurate in most cases. It's just kind of amazing, really. So I'll go ahead and tell you what it is. So the third way that we're going to approximate that integral, or integrals in general, is Simpsons Rule. And for Simpsons Rule, we'll see why this is true in just a minute, but for Simpsons Rule, we need n to be even. You need an even number of subintervals. That's extremely important. But aside from that, it's no harder to use than the trapezoidal rule. Instead of delta x over 2, you have delta x over 3. And then it's almost unbelievable that this makes things better. I'm just adding one more thing in here so you can see the pattern better. So if we had the trapezoidal rule, we'd have all 2's in between. For Simpsons Rule, you change the delta x over 2 to a delta x over 3, and you change every other 2 to a 4. I'm not kidding. That's what you do. So this f of x naught still has a coefficient of 1 in front of it. F of x sub n still has a coefficient of 1 in front of it. But this first 2 you change to a 4. That one stays 2. Then there's a 4, and then there'd be a 2 after that. So maybe I'll write another term, but plus 2 times f of x sub 4. And this keeps going. You alternate 4's and 2's. Because n is even, the next to last one will always be a 4. And then you have a 1 in front of x sub n. So this is clearly no harder to use than the trapezoidal rule. You change this 2 to a 3, and you change every other 2 in this summation to a 4. And yet, Simpsons Rule is stunningly more accurate than the trapezoidal rule or midpoint Riemann sums. So let me tell you how Simpsons rule goes. I will not derive this for you algebraically. It's time-consuming and really has very little value other than as an algebra exercise. But let me just look at a subinterval divided into an interval divided into two subintervals from x0 to x1 and x1 to x2. What the trapezoidal rule does, as I said before, is it approximates the graph by a straight line between the points that you get from your partition. And the trapezoidal rule would approximate this part by a straight line. And then you take the area of the trapezoids and you add. And if the f happens to be negative, the formula still works out right. I should have said that before. What does Simpsons Rule do? Simpsons Rule, so what does the trapezoidal rule use? It uses that 2 points determine a line. And so once you have these 2 points, you know the line between them. Simpsons Rule uses the fact that 3 points determine a parabola. Right? So that may not be clear to you, so let me, that part I'll explain, but the general equation for a parabola, or possibly a parabola, it's true that a could be 0 here, so, but the general equation for a parabola is this. And what I'm claiming is that 3 points determine what A, B, and C have to be. If you want 3 points to satisfy this, that determines A, B, and C. So what do? Well, you want the point x0, f of x0 to satisfy the equation. You want x1, f of x1 to satisfy the equation. You want x2, f of x2 to satisfy the equation. So you say, oh, you have to solve these 3 equations for A, B, and C in terms of x0, f of x0, x1, f of x1, and x2, f of x2. And you can do that. And that's part of the algebra that I don't want to do. But you can find one parabola, or possibly line, that contains those 3 points. The points would have to be collinear for the A to come out to be 0 so that you get a line. But you solve these 3 equations for the 3 unknowns A, B, and C, and that gives you one parabola that of course depends on x0, x1, x2, and f of x0, f of x1, f of x2. And it's the unique parabola that goes through all 3 of these points. So, I don't know, I'll just draw some kind of parabolic-y thing. So, there's this unique parabola that goes through those 3 points. So, then what does Simpsons Rule do? Instead of approximating the curve with a pair of straight lines, it approximates the curve over these 2 subintervals. So it takes 2 subintervals at a time, which is why we need an even number of subintervals in Simpsons Rule. It finds this parabola, and then you integrate. So you find the area under that parabola. Why do we expect this to be more accurate than the trapezoidal rule or than the midpoint Riemann sums? Because your typical graph of a function curves. Straight lines don't curve. Right? The trapezoidal rule or even the midpoint rule use kind of straight lines. But most curves curve. The graphs of most functions curve. And parabolas curve. So it's easy to believe that parabolas would fit the graph better and that your approximation would be better. So what do you get for the area? So you do this. You solve these 3 equations and the 3 unknowns A, B, and C, and then you integrate the resulting polynomial, the resulting quadratic or smaller degree, resulting polynomial of degree 2 or less. You integrate that from x0 to x2, and what you get is the integral from x0 to x2 of the resulting parabola, your parabolic approximation, the curve. If you do this, what you find is that you get delta x. So the delta x hasn't changed. You get delta x over 3 times f of x naught plus 4 times f of x1 plus f of x2. It's kind of miraculous that it comes out to be this simple. The intermediate calculations, the determining of a, b, and c, and then applying the integration, are actually fairly ugly. And yet you get this very nice formula, this delta x over 3, and then f of x naught plus 4 times f of x1 plus f of x2. So how does this give us Simpsons rule? We add together a bunch of things that look like this. So let me just do it once so you can see where these 2's are coming from. The 4's that you're seeing are these 4's, but the 2's come from the overlap, just like they did in the trapezoidal rule. So, right, over our first pair of subintervals, we would approximate the integral by this. But then over the next pair, we would approximate. So that means we start at x2 and go to x4. We would approximate by this. Well, what happens when you add? You pull out the delta x over 3 out in front. You get f of x naught plus 4 times f of x1. But there's an overlap at f of x2, so you get f of x2 plus f of x2, so you get 2 f of x2. And then plus 4 times f of x3. And then if those were all the terms you'd have, plus just 1 times f of x4. Anyway, you end up with this. If you have more subintervals, you keep adding, and on the overlaps, you always get 2 times that value. But those only occur every other time. All right. These are 3 approximation methods. It took a while to state them, and it took a while to explain why you would think of the trapezoidal rule and where Simpsons rule comes from. But now let's actually, maybe I was going to say, now let's actually calculate with them. Let me say something else about this. It's true that calculating these things by hand is no longer of terribly much value. That's not exactly true, but all scientific calculators now, and certainly all computer math systems, can handle calculating definite integrals for you. In fact, they give you an approximation. They use a form of Simpsons rule within extremely large, like I don't know how large extremely large is, but 1,000, 10,000. Your calculators can almost certainly give you values for numerical integrals, for values for definite integrals, by approximating using Simpsons rule. So what's the value of your knowing how to do it? Well, part of the value is that it's just nice for you to appreciate how your calculator is doing this little magic trick of giving you the value of this definite integral. It's really approximating it using Simpsons rule within extremely large. Another part of the value is if you're entering an integral and you hit like one wrong key or something, you might get a wildly wrong answer, and it would be nice if you could at least have some possibility of verifying by hand that the answer your calculator is telling you is close to the right thing. So yes, it's true that these days doing these things by hand is not nearly as important as it used to be, but it's still important. Somebody has to program your calculator, and calculations need to be double-checked in the real world. All right, let's actually see how good or bad these approximations are in a case where we can explicitly calculate the integral. So I'm also going to cheat during this process. I am going to appeal to answers that I already produced on a calculator just for even calculating the decimals that you get from ugly fractions, just to speed things up. We could do them by hand, but that would take quite a while. So let's go back to this integral, which we know equals exactly 0.5. Let's approximate this all three ways with just two subintervals. We need an even number if we're going to use Simpsons Rule, so I'm going to do this first with 2 and then with n equals 4. N equals 8 gets a little, the calculation gets even worse. So the midpoint Riemann sum. All right. Well, actually, let's go ahead and write delta x for us in this problem. B minus, once we have n equals 2, sorry, I should put this down here. Not everywhere in this problem, but once we picked, I said delta x equals 2. N equals 2. Delta x is b minus a. That's 2 minus 1 over 2. That's a half. So that the endpoints of our partition, of our subintervals, so our partition, x naught is 1, and then we go up by a half. So x1 is 1 plus a half, so 3 halves. And x2 is, well, 2. All right. So what's the midpoint Riemann sum? The midpoint Riemann sum is just delta x. So it's just delta x times f of x naught plus x1 over 2 plus f of x1 plus x2 over 2. This is delta x is a half. X naught plus x1, this is 2 halves, 5 halves. So, oh, I should have written up here, the f of x that we're using is, of course, the function that we're integrating. Right. So, x naught plus x1, 2 halves plus 3 halves, 5 halves, divided by 2, 5 fourths. So f of 5 fourths, that is 1 over 5 fourths squared. Plus, then we get 1 over x1 plus x2. So this is 4 halves, 7 fourths. So 1 over 7 fourths squared. And what does this equal? Before I write, I'm writing approximately equals. I'm going to give it to like 12 decimal places, but I'm still going to write approximately equals. I should tell you what the biggest common mistake is in applying any of these rules. In an example where people can produce an antiderivative, sometimes they think that the f in the rule should be the antiderivative of this f. No! You know, if we can find an easy antiderivative, that's not when we want to approximate. We want to use these approximations typically at times when we couldn't produce an antiderivative, so the rules better not use one. They don't. They use the original function, the original integrand. So you get this, and what if you do this on a calculator to 12 decimal places, what you get is 4, 8, 3, 2, 6, 5, 3, 0, 6, 1, 2, 2. I should say another thing. When you're trying to see how accurate an approximation is, what you don't want to do is just give a decimal place or a couple of decimal places. If you're trying to see that, oh, this one's better this approximation's better in the 3rd decimal place than this one, or the 5th decimal place, or the 10th decimal place, well, then you need enough decimal places to see that difference. All right, so there's the midpoint Riemann sum. How much is it off by? It's off by, well, the actual answer is 0.5. So by 0.0177, it's fairly close, not ridiculously close, but fairly close. So let's look at what you get from the trapezoidal rule. In the trapezoidal rule, what you get from this, you get delta x over 2 times f of x naught plus 2 times f of x sub 1 plus f of x sub 2. So this is, all right, delta x is a half, so a half over 2. This is a fourth. F of x naught, that's f of 1, so we get 1 over 1 squared. Okay, yeah, that's 1. Plus 2 times 1 over 3 halves squared. And then plus 1 over f of x sub 2, so 1 over 2 squared. All right, in this one, we can actually say exactly what that is. It's 0.53453472 repeating. All right, so this. Okay, so which one was better, the trapezoidal rule or the midpoint Riemann sum? Right, this is off from 0.5 by 0.017 roughly. But this is off by about twice that. This is from 0.5, this is in the other direction, this is an up, this is, the trapezoidal rule is giving something bigger than 0.5, midpoint Riemann sum is giving something smaller. But the error, or the absolute value of the error, how far away we are, plus or minus, it's, we're only within about 0.034, so kind of double the error that we had from midpoint Riemann sums. That is what you typically expect, that the trapezoidal rule is roughly twice as bad as midpoint Riemann sums. But then we do the amazing thing of just changing a couple of numbers and use Simpsons Rule, and miraculously, sort of, things get better. We take delta x over 3 and f of x naught plus 4 times f of x sub 1 plus f of x sub 2. How could that possibly make things that much better? So delta x, still a half. We're dividing by 3 now, so we get 1/6. And f of x naught hasn't changed. It's 1 over 1 squared. And then we get plus 4 times f of x1, which is 1 over 3 halves squared, plus 1 over 2 squared. And what does this equal? This equals exactly 0.504629 repeating. So how much is Simpsons Rule off? Well, look at it. It's like how close is it to 0.5? It's within like 0.004 and then 629 repeating. So, the error here, we were within about 0.017. Here, 0.034. Here, 0.004. This is much closer for no more work than either one of these. All right. So, yeah, we like Simpsons Rule. Let's go ahead and do n equals 4 and see what we get. I just want to show you what the calculations look like there. N equals 4, then delta x is 2 minus 1 over 4, so it's a fourth. X naught still starts out at 1, but then you go up by a fourth each time. So x naught is 1, so 4/4. And you go up to another fourth, so 5/4. X2 is 6/4, also known as 3 halves. X3 then is 7/4. And then X4 is 8/4, also known as 2. And what do you get for the midpoint Riemann sum? Well, we get delta x, so that's a fourth, and then you just add the values of the f's at the midpoints of the subintervals. So you get 1 over, all right, this is 4 fourths, 9 fourths, 9 eighths, 9 eighths squared, plus 1 over, and then you get 5 fourths plus 6 fourths, 11 fourths, 11 eighths squared. And then you add 1 over 13 eighths squared. You go up 2 again in the thing that we're squaring, or 2 in the numerator of the thing that we're squaring, plus, and then you go 1 over 15 eighths squared. And this is what you get for the midpoint Riemann sum now. And this, I once again appeal to my calculation that I did earlier, is 0.49554793648. Before, we were off by about 0.017. Now we're off by about from the actual value of 0.5 by about 0.0045. So yeah, we got a lot closer by taking twice as many subintervals. And in general, that's what you expect to happen. You expect that as you take more subintervals, your approximation will get better. I'll say it again, technically that doesn't have to happen, but it's what you expect. What about the trapezoidal rule? Well, it looks like this. You take delta x, which is now a fourth, so you get an eighth, and you take f of x naught, so that's 1 over 1 squared, plus 2 times f of x1, that's 1 over 5 fourths squared, plus 2 times f of x2, that's 1 over 3 halves squared, plus 2 times f of x3, which is 1 over 7 fourths squared, plus, and then just 1 times 1 over 2 squared. And what we get is, that this to 12 decimal places is 0.508993764172. What's the point? We're off. The trapezoidal rule is off by about 0.0089, so about 0.009. That's, again, about twice the error that we have in the midpoint Riemann sums, where we're off by about 0.0045. So yeah, the trapezoidal rule, really, there's not much reason to use it unless you just want to use the values of f at the actual partition values, so the endpoints of your subintervals, and don't want to, or maybe you don't have any data about what happens halfway in between them. So that's the only advantage really to the trapezoidal rule, that it actually uses the endpoints of the given subintervals, and the midpoint Riemann sum uses the midpoints. If you didn't have the values of the function f at the midpoints, then yeah, but you had them at the ends of the subintervals, then yeah, you could approximate with the trapezoidal rule, and when you couldn't approximate with the midpoint Riemann sum. But finally, there's Simpsons Rule. Let me just modify what I've got up here. Simpsons Rule, now with n equals 4, what will we get? You get delta x over 3, so you get a 12th. And then, aside from that, we change this to a 4 and this to a 4. And then, I keep calling it stunningly, amazingly, just beautifully, it's just so nice. This comes out to be 0.500417611,489 to 12 decimal places. How much is Simpsons Rule off by? With just 4 subintervals. It's off by 0.0004176. You know, it's very accurate. It's much more accurate than the Midpoint Riemann Sum, which was more accurate than Trapezoidal Rule, off by 0.0045. This is 0.0004. It's like 1/10 the amount of error. And when n is bigger, Simpsons Rule just keeps getting better and better as, in relation to the other two. The fraction of the error gets even better, or gets even smaller. It's, as you can believe, it's probably easy for you to believe, if your calculator does n equals 1,000, or n equals 10,000, or n equals 100,000, that's going to give you 12 decimal places of accuracy, so to the full accuracy of the display of your calculator. Simpsons Rule is what you want to go with in general. All right. This is all I want to say about the numerical approximation techniques. They are tedious, and we did small numbers, 2 and 4. You can imagine when you get up to n equals 8, n equals 10, it's just really painful. Your calculator does it, but still, it's nice to know what your calculator's doing, and now we know we could approximate by hand if we wanted to. In the next section, well, we'll actually start with the next chapter. We're going to look at a whole bunch of different applications of definite integration.